Dr. Vimaladityan Rathina Sabhapati, Professor and Head of the Department of Electronics and Communication Engineering in Aditya Institute of Technology, Coimbatore. Doctorate in the field of crypt analysis in Government College of Technology, Coimbatore. Postdoctoral Fellow in the Department of Information Engineering, University of Padova, Italy. He is very much interested in research area of cryptography, crypt analysis, electromagnetic interference, compatibility, antenna design, wireless sensor network and communication. He has published papers in international journals and international national conferences. He is a reviewer of journals like DRDO, WSEAS, International Journal of Network Security, and also have a membership in professional bodies like CRSI, IACR and Computer Society of India.
Welcome to UGC lecture series, Communication Electronics for Applied Electronics. In the today's session, we are going to discuss about the frequency modulation. In today's class, we are going to see what is frequency modulation and the modulation index of FM and the bandwidth required for transmission of FM signal. Modulation types. We already discussed in the previous session about the modulation types. Basically, there are two types of modulation, amplitude modulation and angle modulation. In the angle modulation, we have further two more types, that is frequency modulation and phase modulation. In case of frequency modulation, the frequency of the carrier is varied in accordance with the message signal amplitude, and in case of phase modulation, the phase of the carrier is varied in accordance to the message signal amplitude. Both frequency modulation and phase modulation is generally called as angle modulation. What is frequency modulation? It is defined as the process by which the frequency of a carrier is varied in accordance with instantaneous value of the modulating voltage or message signal, but phase and amplitude remain same. Let us consider a simple sine wave. This is the message signal, and here we have a carrier signal, and this is the frequency modulated signal. From the definition of frequency modulation, the frequency of the carrier is varied in accordance with the message signal amplitude. So, this is the carrier signal. So, here this one corresponds to the frequency of the carrier, and this is the message signal or modulating signal. What does this frequency modulation says? This frequency gets varied in accordance with the amplitude of the message signal. Here, if we consider the resultant modulated signal, see the difference between this signal and this signal. Here the frequency is varying. If we consider here we have high frequency, and here we have low frequency component, and here we have high frequency, and here we have low frequency. And if you see the amplitude remains same everywhere. That is, the frequency of this carrier is varied with respect to the amplitude. Here the message signal is varying, and based on this variation the frequency varies. So, this is the simple frequency modulated signal. Now, we are going to see how to obtain this frequency modulated signal mathematically, and then we will see the generation of the frequency modulation signals using electronic circuits. Let us consider a carrier signal. Here the carrier signal Vc, which is nothing but Vc cos omega ct plus phi, and a message signal it is Vm cos omega m t. Here this phi gives the phase information of the carrier, but Now, we are not going to consider about this phi in frequency modulation. Here this is the amplitude of the carrier and this is the frequency of the carrier. What does this modulation says? Varying any one of the parameter of the carrier in accordance with the message signal. For example, if you vary this parameter in accordance with the message signal, then it is called as amplitude modulation. If we vary this parameter, which is nothing but the carrier frequency, if we vary this carrier frequency in accordance with the message signal, then it is called as frequency modulation. If we vary this parameter, which is phi, that is, if we vary the phase of the carrier in accordance with the message signal, then it is called as phase modulation. This is the mathematical expression for different modulation techniques. The previous slide says the graphical representation of frequency modulated wave. Now, we are going to see how to generate the frequency modulated signal mathematically. Here we consider the amplitude modulation, what we discussed in the previous sessions. This is the message signal Vm cos omega mt. This sits over the carrier amplitude. If you see this parameter, the carrier amplitude varies in accordance with the message signal amplitude. So, this is amplitude modulated signal. If we consider the frequency modulated signal, that is the carrier with omega c, here the message signal sits over the carrier frequency, that is this parameter alters the carrier frequency. But if you see that amplitude of the carrier remains constant, and of course phase also remains constant, and here we consider phi as 0. Cos omega ct is the frequency of the carrier. Here we are going to vary the frequency. This Vm cos omega t is added here. So, what happens? This entire parameter is the frequency of the carrier. If this is 0, if the message signal is 0, let us take a cos signal. So, at this point, so what about the amplitude of the message signal? 0. So, here this is 0. So, what about the carrier frequency? It is omega c. Suppose if we take the peak of the message signal, either this point or this point, this is the positive peak and this is the negative peak. So, in case of positive peak, so here we have maximum value, that is Vm. So, the frequency gets shifted by some value. So, at this point we have omega c, and at this point we have omega c plus some parameter, which is del omega, and omega c minus del omega. So, during the positive peak, the frequency gets shifted and the frequency is increased, and during the negative peak the frequency gets reduced. So, the frequency of the carrier will vary from omega c to omega c plus del omega, and in the other side it will go reduce to omega c minus del omega. So, this is the total frequency deviation, that is from del omega minus del omega to plus del omega. Again we will see that the graphical representation. If you see the frequency of the modulated signal, this will be same as that of this one, because of the message signal amplitude. If you see here, it is almost 0 at this point. If we consider these points 0, so the frequency of the resultant modulated signal will be almost same as that of the carrier signal. But whereas here in this region the signal is positive and the deviation is also positive, the frequency deviation also positive. Here we have high frequency, and if we consider here, the frequency will be low when compared to the carrier signal frequency because of the negative deviation. Now, we are going to see about how the frequency deviates with respect to the message signal frequency. Let us consider f of t is the frequency of the modulated signal, f c is the frequency of the carrier signal, and here this parameter k f into m of t, this gives the deviation. Here k f is the frequency sensitivity. For 1 volt, how much frequency is shifted? So, that is determined by this k f, that is called as frequency sensitivity, and m of t is the message signal. A complete oscillation occurs whenever theta of t changes by 2 pi radians, and f of t of the angle modulated s of t is determined by del t tends to 0 and is given by f of t equal to 1 by 2 pi the variation of theta of t. In general, if you consider theta equal to omega t, this is the relation between theta and the angular frequency and time t. If you take omega, which is nothing but 2 pi f t. So, what is f? Here we are going to see how this theta varies and it alters the frequency f of t. Comparing the both f of t and integrate on the both sides, we integrate this equation on both sides to get theta of t. So, theta of t is nothing but 2 pi f c t plus 2 pi k f into the integral of m of t dt. Since we are integrating on both sides, so here we have the integration of f of t, and then after simplification this 2 pi will come here. So, this is the resultant theta of t. If you consider this equation, this is the frequency of the carrier, and this one, this includes the message signal, how this angle varies with respect to the message signal. See here, one parameter is added, that is integration is added with the message signal, that is we have to perform integration and then we have to multiply with the frequency sensitivity. Mathematically this is an integration operation, but electronically we have to pass the signal through the a low pass filter. Here this is the mathematical operation, integration, but while implementing the circuit we have to use a low pass filter, because electronically a low pass filter is nothing but an integrator on certain conditions. So, we have considered a cos omega m t as the message signal. So, after integration, so that this becomes sin omega m t or sin 2 pi f m t, and here this parameter k f v m by f m. What is k f? Frequency sensitivity, and v m peak amplitude of the message signal. So, this k f says what is the frequency deviation for 1 volt. Basically the unit of this k f is hertz per volt. For 1 volt, what is the deviation in hertz? So, if you multiply this parameter, we will get the total frequency deviation. So, we call this as a del f, and f m is the message signal frequency. This entire ratio, so this ratio is nothing but the frequency deviation to f m is called as modulation index, that is the ratio of the frequency deviation to the message signal frequency is called as modulation index. This modulation index determines the type of f m. If you consider the modulation index is less than 1 radian, then it is called as narrowband f m, and if the modulation index is greater than 1 radian, then it is called as wideband f m. Let us have a short break. Welcome back after the break. We are discussing about the modulation index. The modulation index is the ratio of frequency deviation to the message signal frequency. So, this is the resultant expression theta of t. After substituting this equation in the modulated signal, this is the resultant frequency modulated signal. This is the mathematical representation of frequency modulated signal. See here, what is this? This is the amplitude of the carrier. This is fixed, this is constant, there is no variation. And if we consider this parameter 2 pi f c t is the frequency of the carrier without any modulation, and if we add this parameter beta sin 2 pi f m t with the frequency of the carrier, then it becomes frequency modulated signal. This frequency modulated signal depends on beta, that is the modulation index, as well as the message signal frequency, whereas this beta depends on this kf frequency sensitivity and the message signal amplitude. So, this modulated signal depends on kf also and the message signal amplitude also. This is the modulation index for FM as well as AM. In case of FM, the ratio of the frequency deviation to message signal frequency, whereas in case of AM, the modulation index is represented by M, which is nothing but the ratio of message signal amplitude to the carrier signal amplitude. And here this M ranges between 0 and 1, that is for AM. If M is 0, unmodulated; if M is 1, 100% modulated; if M is greater than 1, then AM becomes over modulated. But whereas in case of frequency modulation, this beta, based on the value of beta, we can classify this FM as narrowband FM as well as wideband FM. If beta is less than 1 radians, then it is narrowband FM. If it is greater than 1 radians, then it is wideband FM. As we already discussed, this beta is nothing but the ratio of del f to FM. The del f indicates the amount of frequency change in the FM signal from the carrier frequency on either side, that is plus side or minus side. That is, FM signal will have the frequency components between Fc minus del f to Fc plus del f. As we already discussed, depending upon the value of beta, FM signal is classified into narrowband and wideband FM. And the next one parameter, percentage modulation. The percentage modulation is given as the ratio of the actual frequency deviation to maximum allowable frequency deviation. It is expressed in terms of percentage. And the deviation ratio, it is also another parameter that depends on the deviation, frequency deviation and frequency of the message signal. If we consider this deviation ratio, here the ratio of frequency deviation to FM max, that is, this is the maximum frequency of the modulated signal. The ratio of del to FM max is deviation ratio, but if we consider the modulation index, it is nothing but the ratio of frequency deviation to message signal frequency. The deviation ratio is basically the modulation index corresponding to maximum modulating frequency. And the next one is average power in FM. If we take amplitude modulation, the amplitude of the carrier will be varying. So, thereby the power will also vary based on the value of M. Whereas, in case of FM, since the carrier amplitude remains same, hence the transmitting power will be also same. There is no change in the transmitted power, or the transmitted power is independent of the frequency and the modulation index. This is the average power of the unmodulated carrier EC square by 2R. So, EC is the unmodulated carrier amplitude, and after modulation, after performing the modulation, so this is the resultant expression for the frequency modulated wave. So, this is the power of the frequency modulated wave, though the amplitude of the frequency modulated is same. So, this power will be always same as that of this power, this PT will be same as that of PC. So, this slide says about the total power of the modulated wave is equal to sum of the powers of the carrier and the side frequency component. In case of FM, we have infinite number of side bands with respect to the carrier. So, towards the positive side of the carrier and towards the left side of the carrier, we have infinite number of side bands. We will see how many side bands exist in frequency modulation, and the total power is sum of the powers in the side bands. And the next one is the transmission bandwidth required for transmit a frequency modulated wave. As I already said, if we consider the spectrum of FM signal, will have infinite number of side bands. So, what is the bandwidth required to transmit an FM signal? That is given by two rules. One is Carson's rule and another one is universal curve. In case of AM, so what is the bandwidth required to transmit? It is simply 2 FM. So, how that 2 comes? So, that 2 is nothing but the number of side bands. So, one in the upper side band and one in the lower side band. Here in this case, we have to count the number of side bands in the upper side and the lower side, and you simply multiply with the FM. This is n bands and this is n bands, and 2n into FM is the total bandwidth required to transmit an FM signal. We can compute the number of side bands based on the Bessel function with respect to the Bessel table. Other two rules that is used to determine the bandwidths are Carson's rule and universal rule. So, the Carson's rule gives the approximate minimum bandwidth of FM signal, which states that bandwidth is nothing but twice the sum of frequency deviation plus maximum signal frequency available in the message signal, 2 into del plus FM. And the next one is universal rule for determining the bandwidth. As we already discussed, this depends on the number of side bands in the upper side and lower side. So, this gives the bandwidth. Normally, if you take an FM channel occupies 200 kilohertz bandwidth. We will see how. Let us consider a broadcasting station with frequency deviation 75 kilohertz and the maximum signal frequency 15 kilohertz. So, what is this maximum frequency 15 kilohertz? So, this is the maximum frequency of a music signal. Basically, FM is used for entertainment purpose. So, we have to transmit the entire frequency of the songs. So, the maximum frequency available in that music will be 15 kilohertz. So, here FM is 15 kilohertz, and if we consider that frequency deviation is 75 kilohertz, what is the bandwidth required to transmit this signal? So, according to the Carson's rule, 2 into del f plus FM. So, 75 kilohertz plus 15 kilohertz, this is 75 and this is 15. So, totally 90, 2 into 90 gives 180 kilohertz. So, according to the Carson's rule, 180 kilohertz is the bandwidth required to transmit the signal with maximum frequency 15 kilohertz. But in practice 200 kilohertz is allocated to each FM transmitter. So, on this basis the Carson's rule underestimate the transmission bandwidth by 10 percentage, that is here 200 kilohertz is universally accepted bandwidth for transmitting an FM signal, but according to Carson's rule it is only 18 kilohertz. In the today's session we have discussed about the frequency modulation and the modulation index and the transmission bandwidth. If we take the modulation index of an FM, it is the ratio of the frequency deviation to the message signal frequency. But if we consider the modulation index of an AM, it is the ratio of message signal amplitude to the carrier signal amplitude, and the transmission bandwidth required to transmit an FM signal is 2n FM, that is n says the number of sidebands. According to the universal rule this is the bandwidth, but according to the Carson's rule the bandwidth is 2 into del plus FM. And what is meant by modulation index in FM, and what is the difference between modulation index in FM and AM, and state Carson's rule. Thank you.